This noise is constant now. It doesn't go away. Huh?
Better than coming on and off, I guess.
I guess, yeah. So let's start the class. I hope you all have had good weekends, and we are going to finish chapter 4 this week. Today's discussion is going to focus on the turboprop engines. So far, we have covered turbofans, we have covered the regular turbojets. You have seen examples of ramjets in your design and in your homeworks. And we will solve 1 or 2 examples of ramjets on Wednesday's class. So eventually, the introduction to jet engines is going to be done by end of this week, and next week we are going to starting next week we are only going to have 4 weeks, right? Or is it 5 weeks? I'm not sure. It's either 4 or 5.
4 and a quarter.
4 and a quarter.
If you want to count 2 days before Thanksgiving.
Yeah, but I mean, like, how many sessions is that? Is that 10 sessions or 8? Starting next week. It's gonna be 1, 2, 3, 4, 9 sessions. Oh, Thanksgiving Wednesdays. So we have nine lectures in which we are going to cover chapter 11 of this book, which is this topic is off design analysis, and then we'll talk a little bit about rockets. Also, the chapter 5 of the book, which is the UAVs. But the UAV part is not going to take more than a week. It's just an introduction, and I'm not going to quiz you on. I mean, I may quiz you on the material, but it's just explanatory things. You don't have to solve it. If you think your homework 3 is very complicated and it takes a long time, I can give you an extension right now. Don't need an extension? You don't know? Okay, so that's all right. So let's just start the class. If there's no questions. Did you guys? I guess this is not related to class, but did you guys see the new time for the design class? It's gonna be Tuesdays, Thursdays, 1:15 to 2:30.
Is that on the report? Is that on my schedule?
It should be already, but I mean we have submitted the request. I don't know if they've processed it or not.
What was the time?
TR 1:15 to 2:30. So let's talk about the turboprop engine. To analyze the turboprop engine, you have to start with a regular gas generator. If you recall from the earlier part of the chapter, a regular gas generator usually has a compressor, a burner, and a turbine. That's the idea, right? That's as simple as you can put it. And eventually, at the exhaust of the turbine, we still have some leftover energy, some gas that is not expanded to its limit, right? And we have already seen different methods you can use that leftover energy to produce more thrust or to increase the efficiency or whatever, right? We have seen different methods for it. The turboprop analysis comes and takes that leftover energy out of the turbine and gives it to the propeller at the essentially before station 2, before the compressor, right? So, but how do we do that? Well, how do we transfer the energy from the station point? Let's go back to the previous slide and let's discuss it a little bit. The idea is we have some leftover energy outside the turbine, and we want to transfer it to a propeller. right? How do we do this? How can we transfer the energy that is outside of the turbine to a propeller at the station 1 or station 0?
Can you add another shaft?
Add another
Gearbox?
Add another shaft, okay? So essentially what Ryan is suggesting is to add another shaft, which is going to get the energy out of the same turbine we already have, right? That is what you're suggesting, right? What else?
Don't we need to reduce the revolution in order for it to use for turboprop?
You're gonna need a gearbox if that's what you're implying. Yeah, that's for sure. We are gonna need a gearbox because we definitely have to change the shaft power to make it suitable to a propeller, right? What else?
So you said that Ryan said that we would be using the same turbine, right?
Ryan said that, yeah.
Yeah. So I mean, isn't that what we're supposed to be doing? Like we're using the excess energy after that turbine and giving it back to us.
Okay. So essentially, you are elaborating Ryan's point, right? You're agree.
Don't for turboprops, isn't the exit a little different? Maybe that's just because they use the exit for different things. But I feel like you're not so concerned with the energy coming out of or the work coming out of your generator. Like you basically want the flow to be 0 at the exit.
That's the nozzle, not the turbine, right?
Yeah.
You don't want it to be 0, but yeah, you're on the correct path. Okay, so
We already have a shaft with the turbine compressor.
Mm-hmm.
But then if we just put another shaft to the turbine to the propeller, wouldn't that just be again taking from the station 4, station 5, and just still have an excess energy factor in station 5?
Yeah, and Victoria is actually correct, right? We don't want to use the energy that's given to turbine, produced by the turbine, and give it to a propeller. We want to use the excess energy that is that came out of the turbine, right? Does it make sense? So we are already using this energy produced by the turbine. We don't want to divide it between the compressor and the propeller, right? The idea is we have some leftover energy in the gas. We have some expansion potential in the gas coming out of that turbine, and we want to use that, right? So we cannot use the same turbine. Well, what is the solution? Do you have anything to add, Neville?
What's the question?
Okay, so we have a leftover energy. We have some leftover energy, right? And we want to add a propeller here because that's what the turboprop is, right? The question is, how can we transfer this leftover energy to this propeller, right? To rotate the propeller. Some ideas came in. Ryan and Josh and Tyler.
So why do you want to use this energy? Are you short on energy for the propeller? It's excess energy.
We have to provide energy to the propeller, right?
So it's not. So we're assuming the propeller has no energy, and we need to take energy from that excess.
We're not assuming that the propeller has no energy. You have to provide a way to transfer energy to the propeller to rotate it, right?
So you just got a second stage, like a low pressure turbine.
That's it. So essentially, what you add is another turbine after your station 5. That's it. Okay, and I mean, you definitely have to have another shaft. You definitely have to have a gearbox. All of those things are correct, but the only point is that you want to use the leftover energy, right? So whatever, how many, let's say you have 10 stages, it doesn't really happen in turboprop again. Let's say you have 10 turbine stages, you need to have an extra turbine stage to get the to provide some energy to the propeller. Propeller itself, when you install it, doesn't have any energy, right? You have to provide energy to it somehow, right? We do it through a shaft and an LPT, low pressure turbine, right? So that's it. But what is the benefit of a turboprop engine compared to a turbofan? The main benefit you're going to see is the very, very large bypass ratios. So we can have bypass ratios up to 100, which is basically impossible in turbofans, right? But with turbopropeller, you can make your propeller larger and larger and larger, and get higher bypass ratios. And the only structural constraint you're going to see is the propeller design itself. It is not going to change anything about the design of the engine. Okay? Well, what is the main benefit of having a turboprop? Is a higher propulsive efficiency. And we're going to see why that is the case. Let's discuss this a little bit. Why do you think a turboprop engine is going to see a higher propulsive efficiency? Of course, to answer this question, you have to go back to the equation we used for the propulsive efficiency. What was the equation we used? I'm sorry, for the propulsive efficiency.
Total thrust over the change in dynamic.
Thrust power over the changes in kinetic. Okay, so what's going to happen to this? That's for the engine core, right? The thrust power provided. What are we adding here with the propeller? You're adding another thrust generation mechanism, right? So your thrust power is going to be thrust power of the propeller plus the thrust power of an engine, right? So with having a turboprop engine, you are going to have higher propulsive efficiencies. But the problem is that you are very limited in the Mach numbers you can fly your plane. Okay? The turboprops can be usually used in very low Mach numbers, right? Up to 0.3, 0.4. The best ones, the newest with the highest data, with the it's called, I think, actually the advanced turboprop, or ATPs, can go up to Mach numbers 0.6, 0.7, right? In general. So, but the conventional ones can fly up to Mach 0.3, 0.4. The question is why? Why is this happening? And why do we have this limitation?
You don't want the propellers to reach supersonic. So
Okay.
Weight drag.
Exactly. So you don't want your propeller to reach supersonic conditions, and when you are dealing with when your flight Mach number is 0.7, 0.8, what's going to happen is that you're going to see local supersonic conditions on your blade tips, right? Which is not a very desirable thing. Okay, so this is a very small introduction to the turboprop engines and their differences with the regular gas generators. But how can we analyze them? What is the mathematics behind this analysis, right? The fun part of it, right? Okay. The first thing you want to do is to analyze and formulate the propeller itself. Because the rest of the engine we have already analyzed, we have already studied, right? What are the propellers? That's the first step in analyzing your propeller. You have to define the propeller. The propeller is defined as a mean of converting mechanical shaft or torque power efficiently into forward or reverse thrust power in a vehicle. we have two different methods in analyzing a propeller. We are going to mainly focus on the momentum method, or the actuator disk theory. This method was developed by Rankin and Froude, whose names you probably have heard before, right? The Rankin cycle and the Froude number in fluid mechanics. Have you heard about the Froude number in fluid mechanics? You haven't had fluid mechanics. Yeah, so, but these are pretty famous people in thermofluid and aerodynamics in general. The second method we are going to use is the blade element theory, which we are just going to go over an introduction to the blade element theory because it's a little more complicated than the momentum actuator disk theory. But what does this momentum actuator disk theory tell us? It actually replaces your propeller by a circular actuator disk. So we are assuming our propeller is just a disk that is rotating, right? And we want to analyze that, we want to formulate that. So let's do this. Let's start the analysis. Let's say this is your stream tube that covers your propeller here, right? The stream tube is seeing the flight conditions, V naught, P naught, rho naught, and A naught, which is the area of the stream tube that's going to be captured by the propeller. And we have as the station 1 going into the gas generator, V1, rho 1, and A1, right? What is going to happen here, and your actuator disk model, or where you have the propeller in the real life, is that you're going to see a jump in swirl in the fluid. So you can actually assume that the fluid is coming in with no swirl, but after the disk actuator, you're going to see a flood surface, right? Which means that you're going to have some angular velocity in your fluid. Right? We are going to see a jump in angular momentum, and we are going to see a jump in static pressure. Okay, but what is going to be the main driving factor behind the thrust force here among these three? The swirl, angular momentum, and static pressure. What do you think is the change responsible for the thrust power, for the thrust force? We are looking for a change that generates force in this direction, right? Because that's the direction of the thrust, right? So which one of these can generate force in this direction? Static pressure, right? You have the pressure difference between the two. Because of that pressure difference, you're going to push your propeller in this direction. That's it. All right? And because of this analysis, because of this type of analysis, because of the disk analysis, the actuator disk that is replacing your blades, the individual blades are going to be meaningless. We essentially are smearing the individual blade to create a disk all of them, right? That's the idea here. And the shaft power is going to be essentially the shaft power per unit area, or the force per unit, the power per unit area that you're going to see, because we are dealing with a disk with a specific area, right? And each blade is going to be an element of that area, right? Does that make sense? I talked about this. And we're going to call the shaft power disk loading, right? So the next step is to identify the knowns and unknowns of this case before finding the formulas that can help us solve the problem, which is the thrust calculation and the efficiency calculations of this. Let's actually go back here. The known parameters you're going to get in analyzing your propeller is the flight condition, first and foremost, V0, V0, and ρ0, the propeller diameter, which means when you have the propeller diameter, you have the disk area, because we are assuming your propeller is just an actuator disk, right? And the shaft power delivered to the propeller by that LPT, low pressure turbine, right? And the propeller shaft angular speed. We have these these known parameters, but there are 8 unknown parameters. Right? The area, the captured area before inside the stream tube before the propeller or downstream the propeller, the captured area inside the stream tube, upstream the throttle, downstream after the propeller, and the velocities at the propeller and after the propeller, and as well as the angular velocities, right? We are also looking to find the pressures, right? That was one of the concerns here. So we have 8 unknowns, and we want to find it. The first step is to find 8 equations that can help us find these 8 unknowns, right? What is the first thing you do when you want to derive some equations that deals with fluid mechanics or aerodynamics, right? What is the first thing you do? You use the conservation principles, right? Conservation of mass, linear and angular momentum here, and energy, right? So we have actually 4 conservation principles here instead of the regular 3. We have the conservation of linear momentum, and mass, and energy, which we have always had. But another part that is going to be extra here is the conservation of angular momentum, which is present there because of the fluid swirling after the disk. The first thing you want to do is to write the conservation of mass, which tells you that V0 A0 is going to be equal to VP AP, and is going to be equal to V1 A1, right? And keep in mind that we are assuming the flow is inviscid and incompressible, which mainly tells us that the density at the station 0 and the propeller at station 1 is going to stay the same. So from the continuity equation or the conservation of mass equation, we have removed all the densities because they are all equal. Okay? So let me ask you this. For this type of flow, for inviscid incompressible flow, what will be the momentum equation, the linear momentum equation between a station 1 and a station before, prior to the propeller? So between 0 and P, not 0 and P. What will be the momentum equation? Inviscid incompressible flow. Or let me rephrase that question. What is the equation that governs the relationship between the pressures and velocities at the station 0 and the station P for an inviscid incompressible flow? Bernoulli's equation, right? We are dealing with an inviscid incompressible flow. There is no swirl here before the actuator this, so you can essentially write the Bernoulli's equation between the 2 stations. Well, for the station between P prime and 1, in which we have the swirl present, what you want to do is to use a modified version of the Bernoulli's equation, right? So between P prime and P1, we're going to get PP prime plus 1/2 ρ0 V Vp squared plus V theta P prime squared. Vp is the velocity of your fluid at the disk, and V theta P prime is the swirl velocity, the angular velocity after the disk, right? Which is going to be equal to the same thing at the station 1, the swirl velocity, the angular velocity at station 1, and the linear velocity in the x direction at the station 1. And your energy balance is going to give you the relationship between the force that is going to be applied on the propeller and the velocities at the station 1 and station 0. It's the force balance, right? So essentially we are dealing with a jump in momentum here between station 1 and station 0. Does it make sense? Okay, let's move on. The shaft power can be calculated by this equation. We have the force of the propeller multiplied by the V naught, which is the thrust power, it's a power term to recall, plus the changes in momentum. Then actually when we say the shaft power here, we are talking about the shaft power that is provided by the turbine. So here, we are actually calculating the power that is necessary to rotate this propeller, right? Is the thrust power provided plus the momentum jump, right? And in the momentum jump analysis, we are also including the swirl velocity as well, right? So essentially, think of it this way: we are assuming the swirl velocity is actually perpendicular to your linear velocity, and the total velocity at station 1, which is supposed to be, let's say V1 total squared over 2, is going to be equal to the square root. Let's call it V1t is going to be the square root of V1 squared, the linear one, plus V1 theta squared, right? So don't be confused when you say this term, this term. And the idea was, we previously discussed the fact that your thrust power, your thrust is present there because of the jump in static pressure. So we can also find the propeller force, but the changes in static pressure before and after the propeller. But the next equation we want to write, is the angular momentum conservation, which based on the angular momentum conservation, we can actually write the angular momentum conservation for the station 1 and station 2 prime, both of them, right? And it has to be conserved, right? And the angular momentum in your blade is actually also equal to the power that is provided to the propeller, right? If you recall from your previous from your dynamics, I assume, we can find the torque of propeller by taking this integral. And if you do the integration from 0 to R1, which is the radius here, the radius of this string tube, or 0 to RP, which is the radius of the disk itself, we can find the total power generated, okay, omega multiplied by the torque we have over there, which is going to be 2/3 m dot p omega v theta at each station is multiplied by their respective radiuses. Radii. Is there any questions so far?
Is there supposed to be a prime somewhere?
Where?
Where it's like shaft power. You're saying one's before and one's after?
No. So we are talking about these two equations talk about the conservation of angular momentum, right? What is the angular momentum before this? Before the disk? Forget about the equation, just answer my question. We're looking at this. We have fluid swirling here, and we have fluid not swirling before the disk.
Okay.
What will be the angular momentum before the disk? Okay, so we write the conservation of angular momentum for the after the disk condition. We can actually write it for the whole thing, but then it defeats the purpose because we will have an unknown the influence of the disk, right? And these two is going to calculate the thrust power, the power, the shaft power you're going to get at your propeller based on the information you have or you're going to calculate after the propeller or at the station 1, right? They both must give you the same power. Why? Because the idea is your angular momentum is conserved. So your total angular momentum is going to be the same at the station P prime and P1, right? And all of them must be equal to the thrust power, which is the source of your angular, not the thrust, but the shaft power, which is the source of your angular momentum. Does it make sense? So you essentially find this shaft power using your omega, which is the angular velocity of the disk, right? And torque. The propeller torque. But the propeller torque can be calculated at each station based on the information at that station, right? And you can, I don't want to go into this. What we can do is to simplify the momentum equation. We have seen, we have the momentum equation we have for the station between a station P prime and 1, and essentially remove all the swirling velocities, assuming that the swirling velocities are small compared to your flight velocity. And we can also find the shaft power. We are essentially simplifying this equation here, the equation at the top, and the information we get from here. We can find the shaft power, or we can remove the swirl velocity from the shaft power calculation, which we have at the top here. So we have two ways of calculating the propeller force. This arrow should go here. One is using the velocities of the station 1 and station 0. The other one is using the pressures after and before the disk. Which tells you that the pressure jump after and before the disk is going to be equal to the 1/2 rho naught V1 squared minus V naught squared, because these two are equal, right? The propeller force is going to stay the same. Does it make sense? Let's set them equal to each other, and that's going to be it. We are making one assumption here, is that the velocity of the propeller is essentially the average of the two velocities at the station 0 and station 1. To make our life simpler, you can plug this equation here in. This equation here for the thrust power, you can plug that in. And this is what you are going to get for the shaft power. You can play with this a little bit to get to this equation. And the propeller efficiency can be defined as the force, the thrust power of the propeller, we will divide it by the shaft power that is provided to it. And we already have all the formulas we need for all of those things, shaft power and thrust power. Something that you can get out of this equation here on the top is this is going to tell you that the power you are going to need to provide to the propeller can actually be calculated just as a function of the velocity at the station 1 and station 0. All right, station. Is there any questions? Okay, if not, let's move on. Are you guys still writing? No. Okay. We define another efficiency, which is essentially is going to be your efficiency of this efficiency compares the total energy jump, right? M dot v1 squared compared to the shaft power. So essentially, that's efficiency of the propeller in transferring all of the power provided to it to an energy jump, right? Does it make sense? And using that, we can actually find the propeller efficiency as a function of the propulsive efficiency.
Repeat the definition of that efficiency one more time.
Okay, let's do it together. What does the numerator here represent?
Kinetic energy?
What?
Kinetic energy?
Yeah, what does it represent though? Like the kinetic energy at one station minus another station, right? That's it. So what does that the subtraction represent? Energy jump before and after the propeller, right? Okay. What does the denominator represent? Shaft power that is provided to the propeller, right? So we are comparing the efficiency of the propeller, or we are actually comparing how effectively the propeller can change the kinetic energy, right? Can change the energy of the fluid compared to the energy that is provided to it. Does it make sense? Okay, so that's it for the momentum theory of the propeller. Let's talk a little bit about the blade element theory. As mentioned, blade element theory is a little more complex, but it is a little more with aerodynamics and airfoil theory. So it essentially follows the classical airfoil theory, and it says a propeller is a spinning or twisted wing with an angular speed of 2 pi n with a span-wise element in solid body rotation. So we are essentially assuming that each blade is a wing that is rotating, right? Or we are saying that a propeller blade is composed of airfoil sections along the spans that sees the relative flow, and because of seeing that relative flow, it creates local aerodynamic forces and torques. So this is what you're going to see, or this is what you're assuming when you're dealing with the blade element theory. And it is obvious that using this type of analysis can lead to a more robust and more accurate representation of the problem, right? But again, it's a little complicated compared to whatever we have seen before. The momentum theory that we just saw. We have the rotation with the speed omega, right? We have the radius of each propeller, and you have one small element of the area. And as you probably know by now, whenever you see these dRs and dLdFs, you are talking about the small elemental change or small elemental force or whatever, right? That's it. So essentially, to get the final values, you have to make sure that you are taking the appropriate integral, which makes it a little complicated, right? We have some definitions to make here. The first one you want to be aware of is this, is that the aerodynamic lift on the blade element is proportional to the local effective angle of attack, which is composed of a geometric angle of attack and the zero lift angle of attack, as well as an induced angle of attack. I'm pretty sure you are all familiar with all three terms at this point, so we don't need to go over them. But there is one problem with this type of analysis, the blade element theory, that we are not including the three-dimensional, we are not analyzing the three-dimensional aspects of the blade, but we can comfort ourselves with thinking that including the induced angle of attack is actually bringing in some three-dimensional effects on this blade, right? But I'm not going to go through the derivations, but eventually you can actually find the force and the torque, that is force and the torque of the blade, based on the lift and drag that is being exerted by on the blade by the flow. And keep in mind that we are talking about one small element on the blade, right? So we have the derivative of force dF, which is going to be dl cosine of phi, and phi is going to be the effective angle that your blade makes with the plane of rotation. Well, all of these are should be given usually. And then you can find the torque, the small element of torque, as R multiplied by dL sine of phi plus dV cosine of phi. And dL and dd are a function of the span of the chord length of the blade, as well as the lift and drag coefficient of the small element. But what do we want to calculate eventually? Eventually, the idea is to calculate the thrust, right, and the efficiencies. Okay, so we already have the force, so we are already have a representation of thrust there, but we define the elemental efficiency, right? Elemental propeller efficiency as V naught dF divided by omega d tau. omega d tau is that elemental small section angular momentum, right? Which is supposed to be equal to your shaft power, right? Based on the conservation of angular momentum. And on the numerator, you have the thrust power, which is V naught dF. Does it make sense? Okay. So essentially, in an example, I may end up asking you to calculate the thrust using the blade element theory or the momentum theory. Usually, I will ask you to use the momentum theory, but I guess if I want to be mean to you, I will ask you to use the blade element theory. Let me see how it goes. Is there any questions so far? No? Okay, so let's move on. So essentially, all the rest of the stations, all the rest of the stages of the turboprop, we have already seen. The only two new parts is the low pressure turbine and the propellant, right? So if you have a good understanding, we already know how to deal with another stage of the turbine, right? It is just an additional stage, right? But we will talk about that as well in a little bit. But if you already know how to deal with that propeller, we essentially can find the level we are looking for in a turboprop analysis, right? But let's have a summary of the new parameters that are going to be introduced here. The first one is going to be your gearbox efficiency. That's your power of the propeller divided by the power that is provided to your gearbox, right? So essentially, how much of the power goes from the gearbox to the propeller, right? How effective is gearbox in transferring power from the shaft, the LPT shaft, to the propeller shaft. Then we have the propeller efficiency, which is going to be your force power, propeller force power divided by the power provided to the propeller, right? But eventually, we need to calculate the total thrust that is there. It has two parts. The first part is the propeller part, the other part is the core part. How do we calculate the thrust of the gas generator? What was the equation for it? Okay.
So mass flow times the V9, so on.
Minus the mass flow times V1 plus the pressure difference, right? Divided multiplied by the area. So yeah, you should know this by now. But that's alright. You can always go back to it. Yeah. So and we have already talked about calculating the F of the propeller, the force generated by the propeller. But let's take a look at the other part of the turboprop here, which is the low pressure turbine. When you include the low pressure turbine, we are including a station 4.5, right? A station 4 is going to be the entrance of your turbine or the exhaust of the burner, right? And then we're going to have a station 4.5, which is going to be your exit of the main turbine and the entrance of or inlet of the low pressure turbine, right? And then we are going to go to station 5, which is the exhaust of the low pressure turbine, and then we will have the nozzle, which goes from station 5 to station 9. Okay. So we essentially have to rewrite the formulas we already have for the high pressure turbine. This is a very simple, the simplest part. Right, we had the energy balance between the compressor and the turbine. Here, the energy balance is going to be only including the high pressure turbine, right? So the enthalpy change between the station 4 and station 4.5, which you don't see on this TS diagram here, has to be equal to the total enthalpy change at the compressor. Does it make sense? Yes, we are essentially replacing the numbers here, right? Instead of T5, we're going to get T4.5, which is the exhaust of the turbine, and the mechanical efficiency is only referred to the high pressure mechanical efficiency, the high pressure turbine mechanical efficiency. Using this, we can find the enthalpy, total enthalpy at the outlet of the high pressure turbine, right? Which these are all the equations we have already seen. We are just changing the numbers and then and the subscripts. We can also find the pressures, the pressure ratios, and the temperature ratios. Keep in mind that we are going to have a small state efficiency that only relates to high pressure turbine, and we are going to have other efficiency parameters that relates to low pressure turbine, right? So you have to be mindful of all the fact that we have two state turbines here, two different turbines here. Well, how should we deal with the propeller or the efficiency of the low pressure turbine? Essentially, we are going to think of propeller as an external load to the cycle. So the propeller load itself is going to be dealt with as an input to the turboprop analysis. Okay. The efficiency of the low pressure turbine, of course, is the comparison between the actual condition, actual expansion compared to the isentropic expansion, which is going to be exactly the same as the high pressure turbine. So the efficiency of the low pressure turbine is going to be equal to H total enthalpy at the station 4.5 minus the total enthalpy at station 5 divided by the total enthalpy at the station 4.5 minus the station 5 isentropic, the isentropic station 5. Okay. Does this make sense? Like we have seen all of these equations before, the only difference is that we are writing them for a high pressure turbine and a low pressure turbine, right? So the subscript and the station numbers are going to be a little different. Just have to be mindful of that. Okay. Then we also know, we have already seen this, the nozzle efficiency. That is there from station 5 to station 9. We have already seen this, I already talked about this. But then the question is, how can we identify the total power that is available for graph coming out of the high pressure turbine, right? Pretty simple. That's the enthalpy difference between station 4.4, not 5, right? 4.4 and station 9. Does it make sense? That's it. We are trying to get some more expansion out of it, using the low pressure turbine, but the total leftover power that was available to us is going to be this enthalpy change. We can play with the formula, we can change the formula a little bit, and we are going to name that the ideal power that is available for graphs. Is there any questions so far? No? Okay, so one other important parameter that we need to be discussing is how much of that leftover power is going to the propeller. And how can we calculate that? It is called alpha. How can we calculate that? How can we calculate a ratio of the power that is going to the propeller? That essentially you have to compare the expansion you are going to get out of your turbine, the low pressure turbine, which is HT 4.5 minus HT 5, and compare it to the nozzle and total enthalpy change. Does it make sense? It's going to be the amount of essentially power you are stealing from the nozzle and giving to the propeller. And if you are dealing with the ideal conditions, you have to include the isentropic analysis, but the definition is isentropic, right? The definition of this alpha is for the ideal conditions, for the isentropic conditions. So you have to be mindful of that. Okay. And based on what we have seen before, the denominator here is actually can be the ideal power that is available there divided by m.9, and the numerator, as we have seen before, is in the previous slides, is going to be the low pressure turbine power divided by m.9 divided by the efficiency of the low pressure turbine power. So using this alpha, we can find the low pressure turbine power. Can find an equation for that, and using that low pressure turbine power, we can find the propeller efficiency or propeller efficiency power, if you will, here, which is the multiplications of a lot of efficiencies, right? The mechanical efficiency of the low pressure turbine, the gearbox efficiency, and the propeller efficiency multiplied by the low pressure turbine, right? And we can replace this equation with the equation we just tried here and come up with another equation that is going to give us the thrust power, the propeller force power. Is there any questions here? But using the same analysis, we need to find a V9 for the exhaust of the engine, right? Which is going to be a little different from the V9 you already calculated because of the additional stage you are going to get. So we can find the V9. Of course, we can find the V9 with the equations we have already had, which was the comparison between the enthalpy at the station 5 and station 1, 9 multiplied by eta n. But this equation here, this simplification here, is actually makes uniqueness of having the fluid parameters at the station 5, which is the exhaust of the low pressure turbine, right? You can have only the exhaust conditions of the high pressure turbine and calculate your exhaust velocity. Does that make sense? Okay. So after some simplifications, you can find your V9 as this. V9 is going to be equal to the square root of 2 multiplied by 1 minus alpha, eta n ht 4.5 multiplied by 1 minus the pressure ratio to the power gamma t minus 1 over gamma t. Any questions so far? Now, eventually, the goal in these kind of analysis is to find a specific thrust, which in this case, you want to include the effects of propeller as well as the other parts. Your specific thrust for a turboprop engine can be calculated using this equation. Then we have the propeller specific fuel consumption, PSFC instead of TSFC, that we have seen before. That essentially is going to be N.F divided by the power provided to the propeller plus the power provided to the core. And the propeller power, we have seen how to calculate this. It's just a reminder. And the core power, we also have seen this before. How to calculate the core power. And yeah, Is there any questions? No? So let's move on. The thermal efficiency of the whole cycle, of the whole turboprop engine, is defined as here the important energy for us is the power provided to the turbine and to the compressor and the propeller. So instead of the energy jump, we only care about the power that is provided here. Combination of the two power divided by m dot FQR, which is the heat added because of the combustion you have in the burner. And the propulsive efficiency is the total thrust, which includes the propeller thrust and the gas generator thrust divided by the powers. We can also find an optimal ratio here. That alpha represented a ratio of the remaining energy after the turbine that went to the propeller, right, versus the nozzle. Does that make sense? Yeah? We want to have an optimal value for it. What is the optimal value of that ratio? How much of this power, the leftover energy, we want to take and provide to the propeller, right? To get the maximum efficiency out of the system. The proof is in your book. I didn't want to go over the proof, but essentially this is going to be your equation for the optimal alpha. You can assume that all the efficiencies are 1 for all of the systems to have an ideal optimal alpha. And for that ideal optimal alpha, you can actually find it as a function of all the temperature ratios you are going to see. Is there any questions here? Okay, so we went a bit faster than I expected. Maybe a lot faster than I expected. That's all the discussion we are going to have for today. I can give you an example to solve.
Let us take it in. There's no way I have all the formulas written down to solve any example problem.
Okay. Okay.
You go back.
Okay, that's all right. So yeah, that's it for the lecture today. Of course, you can ask any questions if you have any. But and that's it actually for the discussions we're going to have in chapter 4. We have finished the main part of the class essentially. The main, which is the introduction to. I didn't know you hated this class this much, but
I really enjoyed this class.
no, I'm just kidding.
I enjoyed it, but we went from a lot of math to like I can't even write those equations. How am I gonna solve those equations? It's easy arithmetic. It's just like sitting there for hours plugging in numbers.
So the quiz on Friday is we didn't have a quiz last Friday, so the quiz is gonna be on this stuff or is it gonna be on the old stuff?
Probably on the previous week's stuff.
Did you post the lecture slide?
I have already posted.
And you said that for this week we can submit the quiz you were going to submit last
Yes,
week.
yes, because I didn't come to class, so I needed to cut you guys some slack. So on the Wednesday we are going to solve some example problems. What I'm going to do is I'm going to use this webcam here or my own camera to record the lecture, and we're going to use the board. Because I think for my teaching style, using the board is more effective. It suits me better, right? You guys can, you have seen both the slides, so you can
I think we like that one.
Okay. Okay. If that's the case, then I can like try to like transform everything to a
Because
chart
then
number.
we can only write as fast as you can write, so we get more stuff done.
And you only write the important bits.
Exactly.
So then you only write the important bits. You ask us for an equation, I have to go through 150 equations to try and find the one that fits.
Yeah,
the question.
that's true, but we have more equations in this course compared to the flight and orbital mechanics course in general. Okay, so I try to do that. I try to from chapter 5 there is no way we can use the board. We have to use a PowerPoint because it's all concepts and everything. But
So next week we're going into
chapter 5, yeah, chapter 1 week on chapter 5, and then you get a quiz on chapter 5, which is just a simple like explanatory quiz. Then chapter 11 and chapter 12. So we are essentially skipping chapters 6 through 11.
And if we were to have the final before Thanksgiving, do you know when that would be?
Then that would be, I can give you the final either on. Let's actually, since the last time we discussed, Nila was not here. Let me stop this. Let's have this discussion because it's very important, right?